In the Cumbrian Fells, just north of Kendal, a tanker full of liquid chlorine. This will be used to make sure that the water supply leaving this water treatment works is fit to drink. All our water supply comes in the first place from rainfall. There's plenty of that up here in the English Lake District. This is a man-made lake, Haweswater, used to collect the water streaming off the surrounding hills. Millions of gallons of water are held back by the big dam down the valley. The water is carried by pipeline to the Watchgate Water Treatment Works, several miles south, where that chlorine, which will be used to kill any harmful organisms in the water, is being delivered. It's liquid chlorine contained in a steel tank. Precautions have to be taken when it's being piped off into the works. Here's a way in which we can find out if there's any chlorine gas around. If we pour some concentrated aqueous ammonia onto a clock glass, then produce some chlorine in the vicinity, we get white clouds of ammonium chloride particles. The tanker driver uses concentrated ammonia solution to test for possible leaks. A warning board is displayed. There's always a little chlorine trapped between the cap on the end of the filler pipe and the valve to the tank. It causes a little fuming with ammonia. The liquid chlorine in the tanker will be taken off along this yellow pipe. It'll be pushed out by compressed air along the white pipe. Respirators, just in case. More ammonia solution to check for leaks. Now the liquid chlorine can be pumped out. Fresh loads of liquid chlorine are delivered regularly to treat every drop of water coming into the works, to sterilize it and make it safe to drink. It's stored in these yellow tanks. The tanks have load indicators underneath them, which show how much chlorine is left inside. If there were a leakage of chlorine, its mass would start to fall more quickly, giving a warning that something was wrong. And there are other warning indicators as well. Precautions have to be taken anywhere where dangerous substances are being handled. If the chlorine tanks got heated for any reason, the pressure would rise as liquid turned into gas. This would cause discs to burst inside this special valve, releasing the gas into the cylinder in the middle and so reducing the pressure. And just in case any liquid chlorine spills, which would be very dangerous because even a little would quickly evaporate to produce clouds of poisonous gas, there are sills at the bottom of the doors to keep it from trickling outside. And emergency gear is always at hand. The liquid chlorine is gently heated to give gaseous chlorine in these evaporators. Liquid chlorine goes in, the gas comes out. The gas is dissolved in water, and this chlorine solution, chlorine water, is added in carefully controlled quantities to the water that's come down from the hills. Chlorine destroys living organisms in the water. The mixing is carried out at several points, such as this one. Then the treated water passes to the sedimentation and filtration tanks, but we'll talk about this later. Inside this building, at the Watchgate plant of North West Water, they also use another interesting chemical substance to treat the water. These are ozonizers. Air is passed through them, and part of the oxygen it contains is turned into another form of oxygen, an allotrope called ozone, or trioxygen. This is what happens inside the ozonizer. It contains a series of tubes, inside each of which a strong electrical field is produced, through which the air passes. The energy in this electrical field causes some of the oxygen molecules, O2, to split up into separate oxygen atoms. Then the oxygen atoms combine with further oxygen to produce a new molecule, O3. This is the substance ozone. So a mixture of air with a percentage of ozone passes out from the ozonizers and down to control gear below. The ozonized air is now bubbled up through tanks of the water to be treated. Using an inspection port, which can be illuminated by a lamp mounted at another window, we can see it happening. There's also an inspection window at the top of the tanks, on a roof behind. What does the ozone do? Well, ozone is a very reactive form of oxygen. It changes back into ordinary oxygen molecules, O2, and oxygen atoms, O. These oxygen atoms attack, oxidize any traces of substances present in the water which give it a colour, and the water becomes colourless. Here's the untreated water. And here it is after treatment with ozone. Not all the ozone gets used up, so the gases that have bubbled through the water are passed into vessels packed with a reactive form of carbon. This carbon changes the ozone to carbon dioxide, which is harmless, so that the gases can now be safely released into the atmosphere. The ozonization is monitored from the main control room, like all the other processes carried out at the plant, including the use of chlorine, which we've seen, and other procedures as well. Slaked or hydrated lime is added to the water to reduce its acidity. We'll come across this again later on. Here are the instruments for measuring the acidity, the pH. Another substance, sulfur dioxide, is also delivered to the plant. It's used to remove any excess chlorine after the water's been sterilized using chlorine. And all the various pipelines and aqueducts are also controlled from here. The water treated at Watchgate is fairly pure to begin with, and from Haweswater and the other lakes and reservoirs, it travels in covered pipes and aqueducts to the plant. Not all the raw water treated at water treatment works is quite so reliable in quality as the Lake District supply. Let's now look at a plant which takes its water for treatment out of a river which has flowed many miles from the Welsh mountains where it was collected, the River Dee near Chester. This is the intake. A part of the river water flows in here for treatment at another water plant of North West Water. A little of the water is sampled immediately in this small building. It's sampled by fish. Trout live for a while in these tanks, feeding quite naturally on what's in the river water, which flows continually through the tanks. At each end of a tank, there's an electrode. Now, if the fish senses something unusual in the water, say some chemical which isn't normally present, it gets disturbed, and the movement of the muscles of its gills generate tiny electrical impulses which are picked up by the electrodes. The trout stay here, having regular rest periods, until they've grown too big. Then they're put back into the river. The electrodes are connected to an amplifier and a computer, which triggers off an alarm if the fish does get agitated. You can see how the fish we looked at was quite calm and steady until it was disturbed by taking the lid off the tank and switching on our filming lights. There. See the medley of impulses caused by the fish's gills working overtime? This is called biological monitoring. At the same time, other equipment measures things like the amount of ammonia present in the river water and its acidity and so on. These measurements are fed to the treatment plant so that the water can be dealt with as necessary. The river water is filtered to remove any floating solid bodies, then passes to the pump house where powerful electrical pumps drive it on into the treatment plant. This is the North West Water Authority's Huntington Works near Chester, a very large and important treatment plant. Although fairly big items have been removed from the water, it still carries a lot of solid matter in suspension. This has got to be got rid of. Aluminium sulfate solution is added in carefully measured amounts, depending on the amount of water flowing through and how much suspended matter it's carrying with it. And another chemical is also added, a complicated synthetic substance called polyelectrolyte. The result is that the tiny particles of solid matter in the water clump together to form bigger particles. It's called flocculation. Here's a laboratory demonstration. The aluminium sulfate solution and the polyelectrolyte cause tiny particles to come together by electrical forces. After a short time, see how this sample of the river water flocculates, the larger particles formed then sinking to the bottom. This happens in the big flocculation tanks at the treatment plant. The water looks much murkier than it was originally because the tiny invisible particles have flocculated to produce bigger particles. But these big particles will now settle to the bottom, leaving clear water on top. Here's the clear water running off for further treatment. Look at the difference between it and the flocculated water before it's had time to settle. These flocculation tanks are very deep. This is what one looks like when it's empty. The flocculated particles, the floc, settle to the bottom and are piped off as a sludge. Here's what happens to that sludge. It's thickened, allowed to settle a bit more, then pumped into holding tanks. It's then pumped into giant presses where the sludge is squeezed very hard between rows of pads. When practically all the water has been squeezed out, the pressure's released and the cakes left are allowed to drop down below the presses. A rotating screw then carries the broken cake out to waiting lorries. This stuff is harmless but sterile. You couldn't grow anything on it because it contains aluminium compounds. It's spread out in areas like this, taking up much less room than the original wet sludge. Later, it'll be covered over with soil. Even after flocculation, the water from a river still carries very, very tiny particles of solid matter. So it's now filtered through beds of sand in filtration tanks. After a certain time, the tiny spaces between the grains of sand become clogged up by the material filtered out. So the sand is washed, the process being controlled automatically. No more water is run in, and the water level drops to the level of the top of the sand. Then automatically, clean water and air are forced in from the bottom, and this cleans the particles of sand. It's called backwashing. When all the water carrying the material washed off the sand has run away, the tank can be used again to filter the water from the flocculation tanks. Just as at the plant we saw earlier, the water has to be sterilized. At Huntington, instead of using chlorine by itself, they use a mixture of chlorine and sodium chlorate 3 solution. This forms a substance called chlorine dioxide, which is another active oxidizing agent and kills any organisms in the filtered water. And just as at Watchgate, slate lime calcium hydroxide is added in just the right quantities to decrease the acidity of the water so that it's practically neutral. The slate lime's mixed into a slurry with water, and here's where it actually goes into the water being treated. Now the water passes into huge contact tanks. You can see the concrete tops of these tanks, where it's given time for everything to mix so that the sterilisation and neutralisation can take place. Near the control room, there are special smelling bottles, where the water at various stages of treatment can be sniffed by an operator, who will immediately spot anything unusual. And samples are also tasted. As well as water treatment plants' own labs where drinking water quality is continually monitored, there's also a headquarters river laboratory where routine pollution control and river water quality monitoring are carried out, and help is given to the supply labs with any special analyses. Routine sampling can include a chemist carrying out a silver nitrate potassium chromate titration to find the concentration of chloride ions in a water sample from one of the rivers. Rivers sometimes get contaminated by oil from leaking central heating oil tanks at houses nearby, or by diesel oil from, say, pleasure boats. In the laboratory, it's possible to use thin film chromatography to find out what a particular sample is, and therefore where it's come from. At the main laboratory of the Water Authority, they're continually testing water from all the sources in their area, not just from, say, the rivers feeding water treatment plants. Thin film chromatography is a very useful technique for many analytical problems. And the oil is identified. Lowland rivers often flow through areas where there are, for example, chemical works. Sometimes there are leakages of unusual substances into the river. They're much diluted in the river water, but it's important for the water treatment people to know what they are. Very unusual chemicals may need the latest in analytical equipment to identify them. This flame spectrometer is used to identify metal ions. Another advanced technique, gas liquid chromatography, can be used to separate tiny traces of different organic compounds. They're then broken up into charged fragments which pass through magnetic and electrical fields in a mass spectrometer. Different substances produce different groups of charged fragments, ions, which behave differently in the fields. The pattern produced on a screen can then be compared using a computer with the patterns produced by thousands of different organic substances and the best match obtained. In this case, the pattern produced shows that traces of a complicated compound used as a selective weed killer are present. Very occasionally, they stop taking water into the plant until contamination has flowed past. About 75 million gallons of water a day are treated and turned into safe, drinkable water, then pumped out along the mains to the customers. It's all fit to drink, although only a very little of it is actually used for drinking. But whether it's used to drink, or to wash the car, or flush the lavatory, or in factories, all that water gets back into the atmosphere. Then, as rain, it falls again, and some of it will find its way back to the treatment plants, where chemistry plays such a vital part in making possible life as we know it today in the developed nations of the world.